Okay, so let's get started and just let people trickle in. I am Daniela. I work currently at a distributed tracing startup in San Francisco, California, called LightStep. And I'm here today to talk to you all about trace aggregates. Before we get into trace aggregates, I wanted to give everybody an overview. Let me grab my pointer here. A quick overview of the types of data primitives that we work with in observability. We like to call these the 3 data pipes of observability. This is a term that our CEO, Ben Siegelman, came up with recently. You might have heard about the 3 pillars of observability, which is a little bit different because we think about them as data pipes that carry raw data to developers, to software. They're just raw data. Without processing, without further analysis, you cannot get useful insights into your system. And I put a picture of him up here so that you can ask me questions afterwards, but mainly I got a lot of ideas. He helped me a ton with this talk, so it's more of an attribute back to him, to his credit. And also, I think he might be around here afterwards somewhere, so if you don't disagree with me, go yell at him. All right, so a very quick overview just so we're all on the same page. I'm going to move very quickly through this overview since I think most of you know the value of distributed tracing. I think that's well understood now. On the left, you basically have a monolithic service. As more and more modern day architecture moves towards a microservices architecture, you basically need to follow the end-to-end transaction, the end-to-end trace, which is basically highlighted in red up there in both cases. Now, in the second case, in a microservices architecture, tracing is the only way you can get a coherent picture from the perspective of a request. This used to be easy when everything was in one instance or one pod using metrics or logs. With microservices, a trace is really the best way to understand how your requests are going through the system. Okay, so what does a trace look like? Again, very simple. I think most of you probably have seen a visualization of this. We have typically some kind of a client, a web framework that makes RPC calls to a backend server, an API server, and that API server in turn, as you get deeper and deeper into the stack, this is a very well instrumented trace. In this case, you see, a blue, a red RPC, a green RPC, a bunch of gray RPCs, maybe an external service, a third-party vendor. And basically, as you move from left to right, we're seeing a progression in time. Now, with this progression, each single work unit, so each line, each block, in tracing terminology, that's called a span. It's a very context-rich set of data primitives that we can then use later to form all kinds of interesting analysis, which is covered in today's presentation. Okay, so that's just one trace, though. And if you squint your eyes a little bit, this is sort of the shape of many traces you see, kind of a waterfall-y view, a bunch of different spans. And then you look at another one, kind of similar, a little bit different, but the same transaction. And then another one, and then another one, and another one. Now, the problem here is how many do you look at? How do you know that your trace is representative? The key here is we cannot feasibly capture 100% of all transactions. That's just not cost effective, right? For a typical distributed system, probably handling at least thousands of transactions per second. So sampling is inevitable. With sampling, the problem you have is that you don't know whether or not you're looking at a trace that represents the total population. And if you're not careful about it, it might lead you down the wrong path to optimize the wrong thing. So sort of leads us to a very difficult problem as humans. We can't process large amounts of data easily. So it's like, you open 10 tabs, each with a trace, and then you look at maybe 10 of them and you try to deduce, okay, what does the 10 represent? But really what we want to look at is the aggregate analysis over thousands of traces, right? At least thousands of traces. You can probably do tens of thousands. We're going to stick with just a number that's not so humanly possible to process in a short amount of time. It's like hundreds of thousands of traces here. So today there's about 3 topics I want to cover with the types of analysis and the types of insight you can draw from looking at aggregate analysis for many, many traces. But I'm going to focus a lot of my time at the end, including my live demo, on a critical path analysis, which ultimately leads to the root cause of performance analysis and performance regression investigation. Okay, so let's start with something simple like correlations. So this is a symptom of something going wrong. Maybe you got paged. Maybe you deployed something and you're just staring at your metrics dashboard. This is a real dashboard. I just took a screenshot of our internal dashboard. Clearly, there's something wrong here. Something's out of whack. There's a little bump. We don't know what happened. That's around 12 o'clock on a Monday. So this is where the investigation starts. This is your symptom. Ultimately, a bit of a spoiler here. This was the root cause, right? We found the magic graph. If you segment this particular metric by customer, you see that one single customer is inadvertently, in this case, DDoSing one of our servers, basically rendering the box unusable. It's very non-responsive. But in the metrics dashboard, that's not clear. We know something is wrong. We don't know which one to start investigating because they all look very similar. They all lead to the same problem. So how long does it take to get from your symptom to the root cause in this case? It took too long. I don't remember the exact number, at least an hour. I think it took at least an hour. The problem is, to get to this graph, you need to know what to segment by, right? There's a lot of tag values that you associate with your metrics, and knowing that this was the magic value you had to segment by was the first problem. There's a second problem, a much harder one, which is that with low cardinality, in this case, it's a kind of a very fake case that I made with just a select set of customers. There's maybe 5 lines on here. That's just not realistic. For most of your business and services, you're gonna be serving at least hundreds, if not thousands of customers. And it starts to look like this. It's very, very difficult for the human brain to process and to find the anomaly in a graph like this. And this is assuming you know what to segment by, and the tooling that you're using allows you to segment by something that has so many distinct values in the thousands. And most of the case, this is really a problem. It's just not cost effective. Most of the case, it's not even feasible. The tools that we use, a lot of metrics products, literally cannot visualize thousands and tens of thousands of lines on a graph like this. So cardinality is really your fatal flaw with using metrics for root causing a problem like this. So what can you do instead? You can slice the data a slightly different way and really solve the cardinality problem using aggregate traces. So this is a latency histogram. For those of you familiar with histograms, you probably know what this really means. But on the x-axis, you basically have these latency buckets. Each bucket represents a range of latency. So the one I'm pointing at here is between 550 milliseconds and 600 milliseconds. And what you have on the y-axis is the number of traces. I put number of requests here. You can think of it as number of spans, number of traces, it doesn't matter. The number of units of work that was done in your system that fell in this latency bucket. So basically your fast operations are over here, and your really slow operations are all over here. This is just a simple count, right? Okay, so then I drew a line, approximately your P99 is here. So these 3 bars fall within the slowest 1% of all of your requests for your system. Now notice that I've basically segmented my data into 2. I have the slowest 1%, and now I have the rest of the 99%. What can we do here? At this point, we can actually run statistical analysis and try to find defining characteristics of the top 1% slowest requests. What stands out about this top 1% versus the rest? And you're basically doing this ad hoc, right? You're looking at all of your data. You're saying, well, what's causing my tail latencies to be slow? And in this case, again, it's a pretty artificial example. In this case, you have a particular customer. In the previous case, you had to segment by customer ID. In this case, what you basically have is that the defining characteristic is a certain tag value that says customer ID equals to foo bar, and those requests fall largely, though they make a large part of your top 1% of requests. Not all of it. You have some over here, so it's not a perfect correlation, but that's not what we're looking for. We're just looking for the first hint towards where you should go with your investigation. Remember, what you started with is basically nothing. You know something is wrong, you got paged, or you saw something's wrong with your metrics dashboard. You come into a view like this, and you just want the system to run these analysis and suggest to you the characteristics that's abnormal, the characteristics that point at something that might be wrong. Okay, how does this actually apply in a real life scenario? So here is a more real life example. One faulty network card on some random rack in some random data center, right? You don't hit it very often, but once in a while, a request reaches that box and is just completely non-responsive. And that causes your tail latencies. In this case, I actually changed it to P99.9. So this allows you to really explain what's happening with your tail latencies in the 0.1% of your slowest requests. Again, I've segmented here. This is another latency histogram. I've segmented here right at the P99.9 mark. So we're basically looking for defining characteristics of that top 0.1%. And I've overlaid here again in black, circled here. And as you can see, there's actually a strong correlation. This is what we call a correlation coefficient. It's sort of the mathematical representation of how strong of a correlation. And because almost everything falls inside this bucket, we have a very strong correlation. A perfect correlation would be 1. With a single server, with a unique server ID in US West. And this is just really difficult. I mean, imagine having this on a metrics dashboard. First of all, you had to know that this is the server ID you wanted to segment by. And secondly, how many servers are running? I think easily tens of thousands of servers in any of your distributed systems. Imagine looking at a dashboard with tens of thousands of lines and picking out the top 1% that's slightly above the rest, or timing out whenever these requests. And so these are rare occasions, rare occurrences. So catching this on a metrics dashboard is just not very easy. And with analyzing thousands and thousands of traces, it's actually a lot easier because it pops out because you have the end-to-end latency, the end-to-end transaction representation. Okay, so this is sort of where I want to focus a lot of my energy on. So this is a different type of analysis on critical path by looking at many, many traces. So we're back to this single trace view, and another one, and another one. This is a bit of a theme today, looking at many, many traces. So again, if you look at it from a 30,000-foot view, the commonality that you will notice here is that you have this red bar. I've highlighted it to have it really pop. That seems to be the longest in all three of these. And it's probably the case if you look at more, but you can let the computer do the work. You can look at thousands of them and let the computer tell you what your aggregate critical path is. And a critical path is basically the single operation. Sometimes there are multiple, but let's stick with the simple example of a single operation that basically contributes, that makes up the duration of your entire transaction. Meaning that if you shrink, if you're able to optimize that transaction, that operation, if you're able to shrink the length of the red bar, your entire transaction becomes faster. So this is really where you want to focus a lot of your energy and engineering resources to optimize. And that's what an aggregate critical path is. And by looking at thousands of traces, the system can just automatically tell you, here's your critical path. And remember, these spans might belong to different services. So up here might be a service that you own, and you end up making a bunch of RPC calls, and this might be a few hops away, some team that you don't even talk to, and that's what's impacting your service. I'll go more into this in the demo later. Okay, so once you have your critical path, the system tells you need to explain it. Right? You need to explain why it's a critical path, why it's really slow. And that's actually the hard part. Most of the time, I think we generally have an idea where the critical path is actually. So that's not the most valuable thing that the system can tell you. The system can tell you where the critical path is. The harder question that requires oftentimes human intervention to figure out is why. Rarely do we know why the critical path is a critical path. Sometimes it's easy. Sometimes you know that there's a network call or a database call that you simply cannot optimize further. A lot of the time, there is resource contention. And there's a bold statement here that I'm basically making in order to make my demo and my example work, is that, and I think it's true for most of the time, is that nearly all latency issues, remember we're focused on studying latency in this performance investigation, nearly all latency issues are due to some sort of contention. In this example, I'm going to go into it very soon. It's about resource contention, contending for a common resource, a mutex, a lock, basically. Sometimes it's contending for machine resources, CPU, network. Sometimes it's contending for, maybe a cache, maybe a database query. But nearly all latency issues boils down to resource contention. Different processes, different threads wanting access to the same thing. Oops. Okay, so back to the example. I'm basically putting in a very specific example here, already previewed it a little earlier, a mutex acquire operation. So what this is an operation representing how much time this process, this transaction, had to wait for a mutex to become available. And it's capturing it here as a critical path. So generally, I would say in a typical investigation without aggregate analysis, you can find a trace like this, and you're kind of at a dead end here. I mean, you know that there's a contention on the lock. You understand maybe where it is in the code. Maybe you have to go back to the code and try to understand how to break the lock up, how to, basically optimize it further. I would say this is a dead end, and generally without aggregate trace analysis, this is where you stop. But with resource contention analysis, what you really want to understand is what the jam is, why it's so contended for. And sometimes, because many developers contribute to the same code, sometimes you lose sight of this. It's not always easy to understand why a lock takes so long to acquire a lock after you've developed on a complicated program for a little while. So really, you're maybe a car back here. We've all been in this situation. And you want to know what's holding up all that traffic. What's wrong with this? And what's missing in a distributed monitoring environment is a view like this. It's a bird's eye view, a holistic view of what is happening to that contended resource. We can make educated guesses, and often people do when they reach that dead end I was talking about. Maybe it's, in this case, maybe it's an accident, it's a construction. In the lock case, if you have knowledge of the code, you can make guesses, but they're, after all, still guesses. We need data to prove to ourselves that our theories are correct. And in this case, thankfully, there is a solution. I'm going to stay on theme here, trace aggregates, right? Trace aggregate analysis to get to explaining why the resource is being contended for. This is an important slide. It's basically the whole idea around what's happening in the live demo that I'm going to show in a few minutes. Remember, I have thousands of these traces, and for each of those traces, I've used some statistical analysis to find the critical path. That critical path, in my case, is mutex acquire, time spent waiting for that lock. All I need during instrumentation, when I'm acquiring that lock, is to assign a unique ID to that lock, just as a tag value. So you're tagging, remember, spans or context-rich information that you can tag arbitrarily with any number of characteristics. So in this case, I have a unique ID associated with that critical path, and I have many, many traces. So these are all the critical paths from all the other traces. And what you can do is you can actually do a back trace because you have the entire transaction. You can figure out who the parent caller is. So what is the process, what is the operation, what is the function in code that's trying to acquire this lock, and how long did they spend waiting for it, and maybe how long did they spend holding onto the lock. So if you look at, let's say, thousands of these, you're starting to basically get an aggregate analysis of what's contending for this. You're focusing your energy on analyzing the resource that's being contended for. And in this case, before I go into the demo, I want to walk through quickly some terminology that I'm going to be using as a part of the demo. It's kind of made up, but just for the purpose of this talk, we have a very simple concept of the waiters. So, a few threads, they're trying to acquire the lock. Maybe there's a queue, so they're in queue waiting for this lock. And this is the time spent. This is what shows up as that critical path in your trace, the red critical path, as waiters. And maybe at some point, thread 1 eventually gets the lock, holds onto it for some period of time, does some work, releases it, and then passes it to thread 2, who's the next one in queue for this lock. And these are what we call holders. So at any given time, if you're interested in your critical path, you want to understand who's waiting for this and who has held it in the past, or who is currently holding it and how long do they hold it for. And before going into the demo, I want to show you an architecture of what I'm demoing so you have context for the different operations that are happening. So this is my donut as a service architecture. Have this really awesome bakery where I'm selling donuts. and I have an API order service. So what's happening in the demo is I basically have a bunch of a bunch of background orders that's ordering donuts nonstop. In the meantime, they make a payment for the donut, and they come to the fryer service to fry the dough. And the fryer service has a giant mutex on it. You grab the mutex, you fry the donut, then you release the mutex, and this is done serially one by one. After that, it needs to be topped. The topping needs to be added. There's 3 different types of donuts. We have sprinkles, chocolate, and cinnamon. And in this case, before you're able to apply the topping, you also have to grab the topper lock, the different lock, a second lock. You apply the topping, and then you release the lock to let the next donut through. So this is the demo architecture we're going to be working with. I'm going to come over here and start on that demo. So this is just a program I'm running to start sending data to my demo. Maximize this. All right, it's a little tiny here, so let me zoom in. That's a bit better. Okay, so I have these traces. It looks very similar to the ones I've shown before, except that now it's with somewhat real data, at least the data that I'm generating. So you have this background order, and as you can see, I can add a tag here for what topping it is. So this one is a cinnamon, and it makes a request to process a payment, then it fries. This is a fryer operation. And here you can see that it eventually waits on the fryer lock. If I click on this span, you can see that I've tagged this with a fryer lock. Remember that the key to resource contention analysis is that unique ID, which is fryer lock in this case. And then it held on to it for some period of time and eventually passed it off to the topper. Very similarly, has to sprinkle the topping on. So if I click on this lock, you can see now it's a different lock. It's the same operation, mutex acquire, but now it's a different lock. It's the topper lock, and we'll see this show up in the analysis later. And I have a few of these opened just as an example. So this one is a chocolate one, and this one is sprinkles. So if we're just processing this visually, it's very different to really see the differences. I mean, there's definitely some duration differences, but really how many do you look at before you make a conclusion about what's happening? So the point is to use aggregate analysis. So let me just go to my local running instance here. Give it a minute, let Wi-Fi through. Okay, and then I want to be looking at my donut web server service. So I run a query for that. And here at the top, you can see the latency histogram concept that I was talking about earlier, where you can see where your P95 is. Actually, you can even run this on like a smaller set of data. Sorry, my computer is pretty slow. There's the P99. And what we can actually look at is a diagram. It looks very similar to the one in my slides, where you have the donut server, and that's making requests to the fryer and a payment service and a topper in that order, in payment, fryer, and then topper order. The interesting thing here is that it's already highlighting the 2 services that's slowing me down. So the halos, the yellow halos, it's already telling me that that's what I should be looking at. The payment took no time, which we could see that though in the trace. It's a very small amount of payment time spent. Okay, let's go back to this view. And basically with the correlation, remember the correlation I was talking about in terms of looking at many traces, is that you can already see it's telling me that there is a critical path here for donut topper operation mutex acquire. So it's look at all these traces, all the ones that's shown in the histogram, and it knows what operation is holding up, what is my critical path, which I illustrated earlier. So what we really want to see is a mutex view. So I'll click on this tab. Okay, so here's what we got. We have on the top the sprinkle lock. And then there's 2 graphs. There's a waiter graph, remember the waiter, how long the processes spent waiting. And we have a holder graph. This is how long the processes spent holding onto the lock. And then on the bottom, the same thing, waiter and holder, except for the fryer lock. So I think I have enough time to go through the sprinkle case. So in this case, the legend might not be clear to those sitting in the back, but basically we have chocolate, cinnamon, and sprinkle. So in this case, if you look at the waiting time, On average, this is divided by, weighted by the number of threads or the number of instances, the number of orders. On average, they have the same waiting time. In total, though, what is this one? The cinnamon donut spent a lot more time waiting. And this actually makes a lot of sense because I artificially added a lot more cinnamon orders. So in total, it's spending more time, the system is spending more time waiting for cinnamon donut orders, just because there's more orders. So nothing too surprising here. But here it's kind of interesting. Here you can see that in terms of cinnamon versus sprinkles, on average, they hold the lock for about the same amount of time. But for chocolate, and again, this is an artificial demo, so I actually inserted a slightly longer delay for chocolate to hold on to the lock, and it really shows up in this analysis. And it doesn't show up as obvious when you're looking at a single trace, but when you flip it around and do analysis on this resource, the amount of total time, system time spent holding onto a lock for a donut or for a chocolate donut order is way more than the other two, despite cinnamon being sort of the biggest order in terms of count. So let's go back and review basically what's happening here. So you basically have cinnamon, maybe this is your largest customer sending the most data to you, spending a lot of time waiting on chocolate orders. And these might be orthogonal, right? You can totally split out the lock, and this is a very simple conclusion you can draw by just looking at the analysis for about 30 seconds. And you can say, okay, let me split up the lock and have chocolate and cinnamon acquire separate locks so that cinnamon is not impacted by how long chocolate spends topping, even though they're basically different orders. Okay, so I need to wrap up my talk. I was making this slide, and I've gotten a really good advice in the past about how I should schedule my talk, and I had that slide at the beginning where you should always tell your audience what you're going to be talking about. And then the advice I got was that you should always remind your audience the things that you talked about in the talk. So I was in the middle of making this slide. It's very simple. I was just going to copy over the correlation stuff. And then I said, at the end of a very long day, you're going to fly home. You're not going to remember any of this. So my request to you is, I'm not taking that advice, but all I'm doing is please remember trace aggregates as the keywords. It's in the title of my talk. It's the theme of my talk. The next time anybody talks to you about distributed tracing, remember to ask them about what insight you can draw by looking at trace aggregates. If you're evaluating products, if you're just exploring tracing, think about that. Getting to that single trace is not the end of the journey. That's just the beginning. The end is really trying to think about creative ways, novel applications of trace aggregate analysis. And the last thing, in order to get insights from aggregates, you need a lot of traces. I've talked about this, thousands of traces at least. And in order to get that and not feel locked into a certain vendor or a certain product, for your traces to be portable, there was a very exciting merger yesterday announced for OpenTelemetry, which is the next new version, the next major new version for open tracing and open census. So if you're thinking about distributed tracing now, get started with one of them, get started with open tracing. And it's backwards compatible whenever OpenTelemetry comes out. And OpenTelemetry enables you to basically have built-in telemetry features in your cloud-native application. And that's the end. I think I have enough time for a few questions. Thank you. Thank you.
Questions? Hi. In this case, it seems you can only, after the fact, it's kind of when things are slow, you can only have the information for things that you have been tracing for. And it seems in your code, if you're not been tracing for mutex, then you would not know where you spend your time, yeah? And acquiring that mutex is just a part of a call, isn't it? Or it seems to me that actually you had to use your knowledge of, hey, most of the time it's trying to acquire mutex where things go wrong. And then from now on, I'm going to always trace how long I'm waiting and how long I'm holding it. Oh, I see.
Yeah, you're talking about how I get that span with
yes, because
acquire.
It seems if you start from scratch, you have no idea. Now, let's say I'm starting from tracing, I have no idea where my application, maybe, or applications in general are spending time. I won't know what to trace.
Right. I mean, I think instrumentation is sort of a separate talk altogether. But in this case, we basically use a integrated trace block. So whenever you acquire a trace, it's a third-party library, and it's very easy. In this case, I wrote it myself. Whenever I acquire a trace, I start a span, and whenever I get the mutex, I end the span so that I have context. I mean, this is the thing about tracing, is that the primitive is context-rich, and the point is that as developers, we need to get used to adding context to your spans. Which, for metrics and logs, it's a little bit different. You know, metrics typically you have a key and you have a value, and that's it. For tracing, I think adding as much context at development time into your traces can never hurt you, right? Because there is no limit on cardinality, so you might as well add all the tags you can think of. And this is what we internally do as well at LightStep, is we put a lot of rich information into our traces.
Also, especially if you're writing in Go, loads of libraries, anything that you can use may already have inbuilt open tracing. If you pass the context object, they will just automatically do it.
Hey, thanks for the talk. My question is, when looking at the trace aggregates, right, we had that particular operation, that particular span stand out. Do you have a way to aggregate for the similar span happening a lot of time? So let's assume, for instance, the service is multiplexing calls and would make a lot of calls to another service. So instead of like having one call to topping, we would, across the production of a donut, top like 27 times. So they would be represented as separate spans, but in a total time taken in the whole process, they would aggregate to a lot of time. Do the trace aggregates have any capacity to depict that, where this operation that is kind of sliced up into multiple pieces kind of comes together?
Yeah. So for the purposes of my demo, I didn't demonstrate that. The total time is kind of like total CPU time, if you will. It's not total wall clock time. You could, though, slice it up. You could put a restriction also on the time that you're studying the lock for, such that you're only looking at the lock that's literally spending time waiting for other locks because they're contending for this same resource. So in this case, it's just a matter of changing the view of your analysis such that you're aggregating like parallel tasks, and you're not counting that as like a ballooning, wall clock time. But it is still CPU time, even if it's being processed in parallel in your process. Yeah, of course.
In your example, it's at the end, like it was one specific server which was slowing down. So it was among thousands of servers, but it was one tag you were looking at. What if you have like thousands of different tags, different inputs, and that's a combination of 5, 10 different tags, which is actually the culprit? How do you manage to actually find the right combination, which is slowing down the whole system?
Yeah, I think there's maybe two-part question, and I'll answer the first one, which is, the different values, which is, if there's thousands and thousands of servers and you were diligent about instrumentation and you have the unique values, the system is very fast at picking up the one that's wrong. And I think your real question is what happens when there's a combination of tags that's really the problem, not just a single one, but maybe this server combined with this time, or this server combined with this customer. And that's sort of that's actually called multivariate correlation, which I didn't show in this case, but we can do that as well. It just, I think, requires more processing time and statistical analysis. You basically then have to look for combinations of things that's causing issues. And of course, you can't do infinite combinations, and that would take a really long time. So there's optimizations associated with which variables make sense to be combined together. But that's a really enhanced level of analysis that this can definitely support as well.
We have time for one more question. if there is any. Okay, so thank you very much again.
Thanks very much, everybody.